So, in this talk and the following two talks, we will be discussing the proofs in Indian mathematical tradition. So, in this talk, we will be talking about the history of proofs and the idea of Upapatti as they are called in Indian mathematical works, where are they present, and something on what is the understanding of Indian mathematicians as to what an Upapatti, what is the purpose, what it ought to do or what it purports to do. Then we will study few examples of proofs in the earlier Indian texts and come to, of course, the text Yukti Bhasha, which is indeed a collection of proofs. Many of these proofs of Yukti Bhasha will be discussed in the second and the third lecture, and at the end of which we will try to analyze what is the notion of proof in Indian mathematics once again towards the end. Now, while a considerable amount of information is known about Indian mathematics, and it has been known for a fairly long time to modern scholars, there has not been really that much discussion on what is the understanding of Indian mathematicians about the nature of mathematics, what does mathematics deal with, what it is supposed to do, or have Indian philosophers discussed these questions. So, these kind of issues have not been studied or analyzed in any detail. The reason is because we have been so sort of impressed by the achievements of the Indian mathematicians that they did these very nice results. Aryabhatta had this beautiful approximation for square root for the pi, or he had this very nice method for square root, cube root, or Brahmagupta came up with this wonderful formula for the diagonals of a cyclic quadrilateral, or we have this Chakravala. So, these results and achievements of Indian mathematicians occupied a considerable amount of our time and study, and the original works therefore were scanned for the kind of results that they had, and we were not discussing how they were arriving at these results or in what context were they looking at these results. This did not become the subject of serious investigation. One is because traditionally these issues have been dealt with in the commentaries. So, any text in India has to be understood along with its commentaries and along with the successive oral tradition of teaching of that text, and that is what gives you an orientation towards that text and its position in the overall discipline that is being considered and the way this discipline has evolved. So, till very recent times, writing of these commentaries was a very important part of Indian textual Indian scientific tradition, or in all shastras this was a very important thing, and in the traditional scheme of learning these commentaries played a very major role. But since we have been disconnected from that way of studying Indian knowledge systems, we sort of most of the time just look at bare results and then start wondering how did they arrive at it, or did they have any method at all, or did they not have any method at all. And we also start discussing things that maybe Patanjali did not understand Panini correctly, maybe Haradatta did not understand Patanjali correctly, like that. I mean, obviously nobody would have understood his predecessor so thoroughly, that is indeed true, but if he did not understand, there is no reason that we will be able to understand the predecessor much better. So, these are the kind of issues in which we are caught most of the time. So, if we are interested in understanding methodology of Indian mathematics, we have to look at the commentaries much more seriously, and this will apply to most of other disciplines, most of other traditional Indian disciplines also. Now, when modern scholars started studying Indian mathematics, the fact that these books did have various kinds of proofs, the fact that there were commentaries and they contained various proofs was taken note of. Colebrooke's work is the pioneering work of in the translation of Indian mathematical texts. He translated Lilavati, he translated Bijaganita, he translated the two mathematics chapters of Brahmasputa Siddhanta, and Colebrooke's book is filled with footnotes from various commentaries, and occasionally he refers to the kind of demonstrations or upapattis which are contained in the commentaries. Colebrooke says, on the subject of demonstrations, it is to be remarked that the Hindu mathematicians proved propositions both algebraically and geometrically, as is particularly noticed by Bhaskara himself towards the close of his algebra, where he gives both modes of proof of a remarkable method for the solution of the Bhavita problem he is referring to. Similarly, Charles Wish, whose article generated interest about the Kerala School of Mathematics in recent times, this article was written in 1835. In fact, it was submitted as a first a paper to the Madras Literary Society, and later on it was read as a paper in the it was published in the Transaction of Royal Asiatic Society. So, Wish says in his article, he talks about 4 texts, Tantra Sangraha, Yukti Bhasha, Karana Paddhati and Sadratnamala. Except Karana Paddhati, now all these other texts have been fairly good editions, and translations and explanations of these texts are currently available. So, a further account of Yukti Bhasha, the demonstrations of the rules for the quadrature of the circle by infinite series, with the series for the sines, cosines and their demonstrations, will be given in a separate paper. I shall therefore conclude this paper, that is the paper that he is presenting, by submitting a simple and curious proof of the 47th proposition of Euclid, what is generally called the Pythagoras theorem, extracted from the Yukti Bhasha. But Wish did not write any further paper. In fact, there is this detailed manuscript of Wish of this Tantra Sangraha with Shankaracharyar's Malayalam commentary is available with his detailed handwritten notes on one side of the book, which Professor Ram Subramanian had an occasion to copy, and they published some extracts from it of Shankaracharyar's Malayalam commentary a couple of years ago. Now, Wish's paper was widely noted at the time when it was written. It was written in 1835. So, this was considered an important discovery at that time. However, all this was soon forgotten, and there was really no study of Yukti Bhasha for almost 120 years, when C.T. Rajagopal and his collaborators started pioneering articles on proofs in Indian mathematics. And therefore, it is this scant attention paid by modern scholarship of the last 2 centuries to this extensive tradition of commentaries. It is this which has led to a lack of comprehension of methodology of Indian mathematics, and this is often reflected in sort of bland statements that you will find in many of the general history books of mathematics. So, if you open any general history of mathematics, you are likely to come across a statement like this. This I have taken from Maurice Klein. It is a book of about 1000 pages, Mathematical Thought from Ancient to Modern Times. As our survey indicates, the Hindus were interested in and contributed to the arithmetical and computational activities of mathematics rather than to the deductive patterns. Their name for mathematics was Ganita, which means the science of calculation, which is of course correct. There is much good procedure and technical facility, but no evidence that they considered proof at all. They had rules, but apparently no logical scruples. Moreover, no general methods or new viewpoints were arrived at in any area. So, this is a kind of a broad sweep generalization view of Indian mathematics. You will find this in several books. Now, the current books will write it with some more sort of caution and some more subordinate clauses added, but the overall thing will be that to a large extent the way these results were obtained by Indian mathematicians still remain obscure or something like that will be the general content. So, amongst the published works, there are indeed several books which do contain these Upapattis. So, the first is the Bhashya Bhaskara of Aryabhatiya. This contains a few discussions of proofs. The Bhashya of Govindaswamy on Mahabhaskariya, the Vasana Bhashya of Prithudaka Swami on Brahmasputa Siddhanta. This commentary is still not published in entirety, only some sections are available in print. So, the first really book that is of serious discussion of Upapattis is in the Vivarana of Bhaskaracharya on Shishyadhi Vriddhida Tantra of Lalla, the Vasana of Bhaskaracharya on his own Bijaganita, the Vasana of Bhaskaracharya on his own Siddhanta Shiromani. These are indeed commentaries which contain extensive discussion of proofs. Parameshwara's commentary on Govindaswamy's Bhashya, Nilakantha's Aryabhatiya Bhashya, then of course Yukti Bhasha of Jyeshtadeva, Yukti Deepika and Kriya Kramakariya of Shankaracharyar, which we have referred to. Then about 20 years ago, Professor K. V. Sharma published a large number of tracts which were small monographs which contained discussions and proofs of small bits of results on various topics. So, he compiled them and published about 20 such tracts 25 years ago. Buddhi Vilasini of Ganesha Devagyan we have talked about, Krishna Devagyan's Bija Navankura also we have referred to. The Surya Dasa's commentary on Bija Ganita also has Upapattis. Vasana Vartika of Nrisimha Devagyan is a super commentary on Bhaskaracharya's Vasana Bhashya, it is available in print. Marichiya Munishwara is another discussion of Siddhanta Shiromani which contains Upapatti. So, there are indeed a large number of books which have been published. So, if one wants to find out how a particular result was proved, one should first go up and look the available commentaries. Of course, if the proof is not there, one has to search more or one has to look around more. First, because so much has been said about the lack of logical rigor and such thing about Indian mathematicians, we will be forced to sort of give quotations where the Indian mathematicians do say that proving some results are indeed important. If we want to take a mathematical result seriously, a proof is indeed needed. So, here is Krishna Devagya who is writing at somewhere in the beginning of his Bija Navankura. He is saying, he is referring to the result Varga Yogo Dvighna Ghatena Yuto Hinova Yuti Vargo Antara Vargo Bhavatiti Yetadeva Katham. How can we say a squared plus b squared to which 2ab is added or subtracted will lead to a plus b whole square or a minus b whole square? Is there a way of understanding this? Kvachit darshanam to aprayojakam. If we just show some examples of this, that is not really good enough. Anyatha, otherwise, chaturguno rashi ghato yutivargo bhavati ityapi suvacham. Otherwise, 4 times the product of two numbers is equal to the square of the sum of these numbers is also sounds like a proper or a valid result. So, he gives 3-4 examples. 2 into 2 is 4, 4 into 4 is 16, this is also equal to the square of 2 plus 2. Similarly, 3 into 3 is 9, 4 times 9 is 36, this is also the square of 3 plus 3, and again go on, 4 into 4 is 16, 4 times this is 64. So, he is saying why do not we say 4xy is equal to x plus y whole square. Even this appears quite alright because of these examples. 4 into 2 into 2 is equal to 2 plus 2 whole square, 4 into 3 is equal to 3 plus 3 whole square, and actually you can go on, we can give infinite number of examples and therefore we can conclude that this is correct. Tasmat Kvachit darshanam aprayojakam Kvachit vyabhicharasyapi sambhavat. So, verifying some result in a certain number of cases is not really of any great use because there might be a contrary instance. So, the moment I go to 2 into 3, I will find 4 into 2 into 3 is not equal to 2 plus 3 whole square. So, this is vyabhichara, this is a counter example or a deviation from what you are. Ataha varga yogo vignagata yutono yuti vargo antara vargascha bhavatiti atra yuktihi vaktavya iti chet satyam. Therefore, if one says that one should really give a proof for the fact, for the claim that is being made that x plus y whole square is equal to x squared plus 2xy plus y squared. It is indeed true that one needs to prove such a result. Iyam upapattihi ekavarna madhyamaharanante. We will give this proof in the end of the ekavarna madhyamaharana. So, this is basically the translation of the same passage. So, what I am trying to say is that this fact that results in mathematics need to be justified. Merely giving examples to support them is not enough. In mathematics, a certain amount of demonstration is needed, is a well known thing to mathematicians in India. So, one of the earliest discussion of nature of upapattis occurs in the Bhaskara one's commentary of Aryabhatiya. He is referring to the discussion of Aryabhatta that the approximate value of square, the ratio of circumference to diameter is 62832 by 20,000. So, then he is saying that approximate value is being given because the exact value cannot be given. Even Bhaskara one is saying that exact value of pi cannot be given. Then he raises the question, evam manyante sa upaya eva nasti yena sukshma paridhi aniyate nanu chayam asti vishkambha varga dashaguna karani vrittasya parinaho bhavati. It is the corresponding Prakrita version of that. So the square root of 10 is really the accurate value of the circumference of a circle of diameter 1, isn't it true? So why are you saying that a exact value of the ratio of circumference to diameter cannot be given? So then Bhaskara says atrapi kevala evagamaha naivopapattihi. So here also what has been given is only a traditional statement, no justification has been provided. Rupa vishkambhasya dashakaranyah paridhiriti atha manyante pratyakshena pramiyamano rupa vishkambha kshetrasya paridhi dashakaranyah iti. Why are you saying that? Why don't you measure the circumference and immediately conclude that it is square root of 10? Naitat, this is not possible. Aparibhashita pramanatvat karanina. Square root of 10 is a karani, it is an inexact quantity, one cannot really determine its exact value. So like that he goes on to give an argument that indeed one has to provide a proof for the fact that certain amount is this ratio of circumference to the diameter. So the fact that the mathematical result need to be demonstrated is fairly clear in the commentaries. Now the book that gives a set of demonstrations, how does it view what these demonstrations are supposed to do? So in Siddhanta Shiromani, in the Gola Adhyaya, while beginning, Bhaskara tells us what upapattis, the word for proofs, yukti, upapatti are the two words used for proofs in Indian mathematics. So what these upapattis are supposed to do? So this verse, madhyadyam jusadam yadatra ganitam tasya upapattim vina praudhim praudha sabasu naiti ganakaha nisamshayo na swayam. I quoted this in the introductory lecture also, that but for whatever that has been discussed in this Graha Ganita section of astronomy, starting from the Madhyamadikara is the first chapter of the Graha Ganita section of astronomy. So whatever is discussed without proofs, without upapatti, ganakaha, a mathematician, praudhim praudha sabasi naiti, praudha sabasu, he will not be considered as a scholarly mathematician in an assembly of scholarly mathematicians. Nisamshayo na swayam, he will not be free of doubts about the methods and procedures and the results that he is dealing with. So these are the two kinds of handicaps that somebody who does not know proofs will automatically face. The same thing is repeated by Ganesh Daivagnya while starting his commentary on Lilavati, the commentary Buddhi Vilasini, which has a lot of upapattis. Vyakte va vyakta sangye yaduditam akhilam nopapattim vinatat. In both Vyakta Ganita and in Avyakta Ganita, that is both in arithmetic and geometry and in also in algebra, whatever is said without upapatti, nirbhranto vadutetam suganaka sadasi praudhatam naiti chayam, that one will not be considered as a well versed mathematician in an assembly of good mathematicians. Nirbhrantova, nor will he be without confusion about the results and procedure. So this is the kind of focus that has been put on upapattis in Indian mathematics. Upapattis are important, they need to be given, and main purpose is to see that the rest of the mathematicians accept the argument that you are given, so the result becomes a valid result in the community of mathematicians, and it will enable you to be free of how to perform the particular operation or particular result or the particular procedure. So that also a proof will enable. Without the proof, there may be so many confusions about what that original rule is meaning. But now this is very, very different. I mean, if you see the first chapter of the famous commentary of Proclus on Euclid's elements, you will see what proof is supposed to do. The proof is supposed to do a very unambiguous and irrefutable demonstration of the result stated by the text, that it has to once and for all establish in an uncontestable manner the truth of the proposition stated in the text. So that is a very different ideal that does not find a central focus in the discussion of the Indian mathematicians. Now how do they actually prove results? So what does Bhaskara say about these proofs? in the Bijaganita Vasana, Bhaskara gives a proof of this Pythagoras theorem or the Bhujakoti Karna Nyaya, and he says there are two kinds of ways in which you can prove Kshetragata, Rashigata. Kshetragata is geometrical, Rashigata is algebraic. Tatra Kshetragatochyate. So first I will explain the geometrical. Then after some time he says Atra Rashigato Upavatihi Uchyate. So then he will give the algebraic. Sapi Kshetra Mula Antarbhuta. That is also based upon geometry only. Iyameva Kriya Purvacharyahi Sankshipta Pathena Nibaddha. So this Upapatti is something which has been passed down by tradition, by the oral tradition of teaching by generation to generation. And of course he says the geometrical proof is somewhat more complex, for them the algebraic proof is to be given. So let us see what is the geometrical proof and the algebraic proof that Bhaskara gives for the Bhujakoti Karna Nyaya. So the problem is that in a right angle triangle with sides 15 and 20, what is the hypotenuse? Tithi Nakhaihi Tulye 15, Tithi Nakha is 20. Kashruti, what is the hypotenuse? Upapattischa Rudhasya Ganitasya Kathyatam. So give us also the traditional method of proof, or the traditional proof for this traditional method of calculation. So this is the way Bhaskara is explained. Let us not go into the details here. It can be read. Basically all that Bhaskara is doing is drop this perpendicular, you want to calculate this hypotenuse. The basic, this is the right angle of the right angle triangle. So this right angle triangle itself is similar to each of these sub triangles that you obtain. So you use the similar triangles and obtain both these abadhas, this side and this side. So the abadha this side will turn out to be 225 by Ya, if this Ya is the length of this hypotenuse. The abadha on this side is 400 by Ya, square of this by this. So the hypotenuse itself is the sum of the two, and so you will calculate the base to be 25. This is the essence of the geometrical proof given by Bhaskara, and the argument goes like this using the Trairashika, basically the principle of similar triangles. Now then he says, let me give the algebraic demonstration, and as he himself said, the algebraic demonstration is also based upon the, after all you are proving a result in geometry, the algebraic demonstration is also based upon the figures. And essentially all that Bhaskara is doing is, if this is our right angle triangle, construct a square from the hypotenuse of this right angle triangle and put this put the hypotenuse of the right angle triangles in such a way that in the center you are left with another smaller square. And so essentially what you are doing is, you are having this A minus B whole square plus 2AB is equal to A square plus B square, and this 2AB is actually 4 times half AB. So this is essentially the algebra. So this is the algebraic relation that is used in proving. Here is a minus B whole squared, each of these triangles is half AB, so you have 4 times half AB, and the sum of A minus B whole squared plus 4 times half AB is equal to A squared plus B squared. Therefore this larger square is actually equal to A squared plus B squared. So the hypotenuse squared is equal to sum of the Bhuja square and Koti square. So it is called algebraic because this algebraic identity is employed in proving this. So from the Shulba Sutra times, algebra and geometry have closely intertwined in discovering an algebraic result, and even in expressing an algebraic result, a geometrical result. Algebra is employed in a very crucial way, and geometrical arguments are also made to discover algebraic identities. Now let us go to the proof of something else. In Bhaskara's Bijaganita, the Kuttaka Adhyaya, there is a detailed discussion by Krishna Daivagnya of the justification of the Kuttaka process. So how does Krishna Daivagnya justify the Kuttaka process? So what is the Kuttaka procedure? That is for solving the equation Ax plus C by B is equal to Y. A, C and B are given integers, X and Y are to be determined for integral values. That is the Kuttaka problem. A is called the Bhajya, B is called the Bhajaka, C is called the kshepa, and X is called the guna, Y is called the labdhi. These are the technical terms for all these quantities in Kuttaka. So what does Krishna do? Krishna Daivalya first shows that X and Y do not change if we factor all the three numbers A, B, C by the same factor. Then he shows that if A and B have a common factor, then the above equation will not have a solution unless C is also divisible by the same factor. This you already now know that the GCD of the coefficients of X and Y should divide the kshepa, then only the Kuttaka problem has a solution. Then he gives a proof that the mutual division of A and B does lead to the greatest common divisor at some stage. So the so called Euclidean algorithm. So you can see that there is a sequence of argument going on in Upapatti, like the way we do in proving any argument in mathematics that we are familiar with. Krishna then gives a detailed justification of the Kuttaka method itself. What is the Kuttaka method involved? That you make a valli, and that is based upon a detailed analysis of the operations in reverse. This is called Vyasta Vidhi. So at each stage what Krishna shows is that you are obtaining solution for the Kuttaka problem for the successive pairs of remainders which appear when you divide A by B. So when you are dividing A by B, so some coefficient A naught will appear, A naught B. So you will just get the first remainder, then you divide R1, so A1 will appear, A1 R1, a remainder R2 will appear. So for each of these successive remainders, the Kuttaka problem that you will appear, when you go up in the valley, you will be solving the problem with the Kuttaka problem with the successive remainders. That is what is Kuttana. The problem with AB is converted to problem with R1 R2, then problem with R2 R3, problem with R4 R5, and ultimately comes to very small remainders. So you are either able to guess the solution or you can work out the solution. So that is what Krishna is explaining, and then he will also tell you if you have odd number of steps you go in a particular way, if there is an even number of steps you go in a particular way. So the proof of each and every one of these is considered in detail. So as an illustration, Krishna considers this equation 173x plus 3 by 71. While making the argument, the illustration will run parallel. So he will keep an illustration and make the argument. So in the mutual division of 173 and 71, the quotients are 2, 2, 3 and 2. The remainders are 31, 9, 4 and 1. So when we do the reverse operation with Valli, 2, 2, 3, 2, 1, followed by the kshepa is 3, and put a 0 below that, right, in the end. So Krishna shows that in the first level you get 6 and 3 as the labdhi and guna in the Valli when you clear the Valli, and they will satisfy the equation 9 into 3 minus 3 by 4 is equal to 6. So the quantities involved here 9 and 4 are essentially the two remainders which appear here. In the next step you will have a Kuttaka problem solution with the two remainders 31 and 9. The next guna and labdhi will solve the Kuttaka problem with these two remainders, and finally you will get the solution for the Kuttaka problem with 173 and 71. So the reverse operation in Valli is essentially solutions with the Kuttaka problem with the reminders, successive reminders that appear here. This is at the crux of the argument in proving that the Kuttaka procedure works. Now we will come to another aspect of proof in Indian mathematics. This is an interesting philosophical issue which seems to be operative here in Indian mathematical tradition. Most of you who would have seen proofs in standard geometry texts might clearly be aware that one of the most commonly met with arguments is what is called the proof by contradiction. What is proof by contradiction? It is also called reductio ad absurdum. What is that? So whenever you want to prove a proposition, you assume that the opposite of that proposition to be true for the time being, and then argue and obtain a result which is in contradiction either with what you have assumed or with any of the results that you have already proved or with any one of your starting postulates. Therefore, by assuming the contrary of what you want to prove to be true, you arrive at a contradiction, and therefore that the assumption that the contrary of what you wanted to be proved is not justified, and therefore the opposite of that, that is the proposition that you want to be proved, has been proved by you. So this kind of an argument is called tarka in Indian logic. Indian logic is Nyaya Shastra. So this kind of an argument is called tarka. And such arguments do appear in Indian mathematical texts in some simple context. So I have taken the simplest of such arguments to show that a negative number does not have a square. So this is the argument of Krishna Daivagya, to show that a negative number does not have a square root. The argument is very simple. Assume that a positive number is a square root of negative number, it cannot be, square of that is positive. Assume a negative number to be square of a negative number, that cannot be, its square is positive. So there is really no number which you know which is the square root of a negative number, therefore a negative number does not have square. This is a standard argument of proof by contradiction, and this is employed. So nanu runankaha kuto vargo na bhavati nahi raja nirdesha. Why is it that a negative number is not a square? It is not a royal fiat. Satyam runankam vargam vadata bhavata kasya sa varga iti vaktavyam. You who are arguing that a negative number is a square, you should tell me whose square it is. Na tavad dhanankasya, it cannot be a square of positive number because of the rule samadvighato hi varga, because square of a positive number is positive. Napi rinankasya, it cannot be square of a negative number. Tatrapi swamadvighatartham rinankena rinanke gunite dhanameva vargo bhavet. They are also negative, negative is positive. Ityuktatvat evam sati, that being the case, kathamapi tam ankam na pashyamo yasya vargaha kshayo bhavet. So we are not able to see that number whose square is negative. So it is a standard. But while this kind of an argument is commonly used, you do not see an argument in any of the Indian mathematical texts, at least I have not seen one, where you are proving the existence of something, say the Chakravala process. It would be fairly easy for people to construct a proof where, by assuming that the Chakravala process does not lead to a solution, you come up with a contradiction of something that you already know, and therefore you say you have proved that the Chakravala process leads to a solution. So to prove the existence of some quantity which is by proof of contradiction is not something that is commonly met with, and I am trying to tell you that this is fairly in tune with the larger principles of Indian logic, the way, or Indian philosophy. This tarka, while it is useful, in fact tarka is used in the what is called as a sieve in Anumana Pramana, that when you want to establish an invariable concomitancy vyapti between some hetu and a sadhya, you try to refine that hetu further and further by the use of tarka argument, that this hetu may not really be giving to that sadhya. People who know Indian logic will see that that is the context in which tarka is used. So tarka is used as an auxiliary way of arguing. It is not given a status of an independent pramana. What does that mean? That anything that is established by tarka, which in principle cannot be established through the other direct means of verification, will not be given a state of validly established result. So it is not an independent pramana, it is only as an aid to other pramanas. So basically the Indian mathematicians seem to be using reductio ad absurdum kind of arguments, if at all they use, which are very few, far in between, mainly to show the non-existence or impossibility of certain things. They do not seem to have used it at all to show the existence of quantities, which existence is not possible to be demonstrated via other means. That if you already know what the solution is, you do not need the reductio ad absurdum. In the morning a question came in to discuss the way Archimedes proved the argument that the infinite series 1 by 4 plus 1 by 4 square etc. adds up to 1 by 3. This was in a specific geometrical context, in a geometrical construction. So what Archimedes is showing is, let me assume that the sum of all these figures is larger than that other figure, then he will show a contradiction. Let me show that the sum of all these figures is smaller than that sum, and then he shows a contradiction. This is a this is called the double reductio ad absurdum argument, that this sum can neither be larger nor it be smaller, and therefore it has to be equal. Whereas you show by successive smaller and difference between the result that you want to prove and the successive terms of summation become smaller and smaller, and you are actually going to the result that you are wanting. So that is the kind of proofs that you find in Indian text. There is in fact an even larger principle in Indian logic. It is that you do not grant validity to any scheme of inference where a premise which is already known to be false is used to arrive at a conclusion, and furthermore you do not allow in any discourse which is logically considered rigorous terms which you know are empty, terms which are meaningless, like a square circle or a rabbit's horn is the one that is very commonly used, Shashashringa. The insistence on not using these unreferentiated or undenoteable terms is so deep that one is willing to even accept a contradiction rather than use these terms. So this is the major issue. This is a summary. The original work has a detailed discussion which is found in Udayana's Atma Tattva Viveka, or you can pick up Udayana's Atma Tattva Viveka and see this discussion. The discussion is very simple. The Nayayika is saying you should not use any statement which uses fictitious entity is not a valid statement. So then the opponent asks, you have already made a statement using a fictitious entity, so what are you talking about? So he says, I am saying something meaningful, if you do not want to understand it, that is alright, but I will live with this contradiction of not using fictitious entities in my discourse, but I will not allow still the fictitious entities to be used. So we are willing to live with the contradiction, that the contradiction is in the statement that rules out the use of these fictitious entities. So that contradiction is alright, rather than using these fictitious entities in the argument. Now this issue of contradiction is very special in traditions which base all their arguments on reductio ad absurdum techniques. Because what are reductio ad absurdum? The moment you find a contradiction, the opposite of the premise is true, and the moment your logical system has a contradiction, all proposition becomes valid. In a logical system where a proposition P and not P are both true, then from P and not P you can imply any Q, and this is always a universally valid proposition. So these systems of logic which use this kind of reductio ad absurdum to the sort of limit, they are always worried about contradictions in their systems of logic. Okay, now with that interlude, let us come to Yukti Bhasha, the discussion of proofs contained in Yukti Bhasha. Today I will just give, yes ma'am.
Can you please state the etymology of the word upapatti, and can you tell us what is the difference between upapatti and pramana?
Pramana is a means of acquiring valid knowledge. So prama is valid knowledge, pramakarana is pramana, that what leads you to valid knowledge is pramana. So the means of valid knowledge are in ordinary understanding, observation, pratyaksha, argument and generalization from known observation, etc., that is called anumana. Then some differences, then what is called established, well established tradition, that is agama. Then different schools of philosophy have their own other definitions of pramana, upamana and arthapatti, and there are other kinds of pramanas. This is what is pramana in simple terms. Now upapatti is upapadyate, detailed derivation of that we will leave it to the lecture of Professor Ram Subramanian, that you are going and arriving at the, you have established the result or you are arriving at the result. So that is I mean a loose sense of QED. So the most detailed exposition of upapattis in Indian mathematics is found in Yukti Bhasha of Jeshtadeva. So Jeshtadeva says the purpose is to present the rationales of the results and procedures outlined in Tantra Sangraha. Many of these are given in Sanskrit also in the works of Shankaravarya. Yukti Bhasha has 15 chapters. The first 5 mathematics chapters deal with numbers, logistics, fractions, rule of 3 and solutions of indeterminate equation. The chapter 6 and 7 of the mathematics part are the crucial ones. Chapter 6 deals with the Paridhi Vyasa Sambandha. It presents the derivation of Madhava series for pi, derivation of binomial series, the derivation of this estimate of the sum 1 to the power k etc. plus n to the power k for large n, and then derivation of the end correction terms and a transformed series. Chapter 7 deals with the Jyanayana or computation of R signs. It presents a derivation of the second order interpolation formula of Madhava. I think that will be covered in one of the trigonometry talks. This is followed by derivation of the Madhava series for R sign and R word sign. In the end, it has a detailed discussion of cyclic quadrilaterals and also the proof of surface area and volume of a sphere. The astronomy part has 7 chapters which gives detailed demonstration of all the results of spherical astronomy. Perhaps you will get a glimpse of the way Indians, the sophisticated way the Kerala astronomers work with spherical trigonometry in one of the lectures that will follow. So, first is the Yukti Bhasha proof of Bhuja Koti Karnanyaya. So, we saw 2 proofs of Bhaskara. This is the proof of Yukti Bhasha, very simple. This is 1 square ABCD BPQR. This is the Koti square, ABCD is the Bhuja square. Assume that Bhuja is smaller. Now, make your AM is equal to Koti. So, your MP will be equal to Bhuja, that is mark this point M such that MP is the same as AB. Then join MP, join MD, construct the square on MD. Now, the constructing the square on MD, this procedure is similar to the Shulba Sutra procedure for adding 2 squares as it was pointed out in the lecture on Shulba Sutras. Then how to show that this square, this MD squared is equal to AM squared plus AD squared, very simple. At the point D, cut this triangle AMD and place it on DCT, and at the point Q, cut this triangle MPQ, rotate it and place it on QRT. Then you have shown that this square is equal to the sum of those 2 other squares. So, actually it involves cutting and repasting. So, this was another feature of all the Indian mathematical arguments, that they could involve movement of the physical objects, cutting of the object. Then even many of the proofs, say I mentioned Krishna Daivagya's proof of minus into minus is plus, by using that let the direction of moving eastwards be taken as positive, direction of moving westwards be taken as negative, and with that we will be able to show that plus 5 minus of minus 3 is equal to plus 8 and things like that. So, even physical arguments of various kinds are acceptable as proofs as long as one is systematic and one is explained. Surprisingly, I should mention that this proof which is available in the available editions of Yukti Bhasha is different from the proof Charles Wish has given in his paper, saying that this is the proof that I have found in Yukti Bhasha. So, that still remains a mystery. Now, there is another complex geometrical proof that you find in Yukti Bhasha. This is the method of approximating the circumference of a circle by a square which is circumscribing it, and then dividing the square in such a way that you have a regular octagon, then dividing it in such a way such that you have a regular polygon of 16 sides. Again, Kriyakramakari gives a collection of verses due to Madhava which seem to be explaining this method. So, Madhava, who gave the infinite series, also has summarized this method, which is the classic old method of trying to estimate the circumference of a circle by the sides, summing the sides of an inscribed or a circumscribed polygon with large enough number of sides. So, the method is as given in Yukti Bhasha is like this: you take this square which is 1/4 of the square which is actually circumscribing the circle. So, the side of this particular square is right now this is R, but the bigger square which is a circumscribing circle has side 2R. Now the point at which OA1 meets C1, Yukti Bhasha says draw this line A2 C1 B2 which is parallel to ES, east south direction. So instead of saying draw the tangent, which they do not say, this is the way they are explaining. And then it says okay, it goes and meets this side EA1 A2, join OA2. Then this OA2 meets at the point C2. Now draw A3 C2 B3 which is parallel to C1E, and like that you go on. So this EA2 will be the side of a circumscribing octagon, EA3 will be a side of a circumscribing polygon of 16 sides. So this complex geometrical arguments are indeed dealt with in Yukti Bhasha. Now the rest of the argument is using right angle triangles and similar triangles, estimating EA2, EA3. So EA1 is the half of the side of the circumscribing square, EA2 is half of the, EA1 is half the side of the circumscribing square, EA2 is half the side of the circumscribing octagon. Octagon will look like this. Here the octagon, this is the part of the octagon, it will go like that. So this is half of the side of the circumscribing octagon. EA3 is half the side of the circumscribing 16 sided polygon. The corresponding karnas are OA2, OA1, OA3. So the corresponding karnas are denoted by K1, K2, K3. The corresponding abhadas, the abhadas are the intercepts D1A1, D2A2, D3A3. When you have the first one, this D2A2, D1A1 will be the abhada, that is in this right angle triangle, D2A2 will be the abhada in this triangle, and similarly D3 is not shown there. So those are the abhadas which will come handy in doing this calculation. They are given by the following. Then you have a series of recurrence relations that you see which are derived from the geometrical argument. So L2, K2 and A2 can be defined or determined in terms of L1, K1, and so first L2 is determined in terms of L1, K, K1 and A1, then K2 is determined, then A2 is determined. So L2, K2, A2 is determined, then you go on determine the side of the regular hexagon. So given Ln, Kn, An, Ln plus 1, Kn plus 1, An plus 1 can be determined, and in fact if you study the process, the recurrence relation seems to be something like this, and initial value L1 is R itself, half the side of circumscribing square, L2 will be root 2 minus 1 into R, and so on. So you keep on using this relation, you will obtain half the side of circumscribing polygon of larger and larger side, and from that you find out the circumference of the polygon, take it as an approximation to the circumference of the square. And Kriya Kamakari says evam yavadabhishtam sukshmatam apadaitum shakyam. You can go, if you are like Al-Kashi, you have patience, you can calculate pi to 16 decimal places, there is really no problem. So I think for today I have covered the tradition of proofs in Indian mathematics from more ancient times. In the next talk I will discuss the proofs as found in Yukti Bhasha of the results of Madhava. That will be tomorrow on Monday.